Today we're going to look at the Crout decomposition. Recall that when we want to solve a system of linear equations with invertible coefficient matrix A, we often want to decompose A into a product of a lower triangular matrix L and an upper triangular matrix U. This is known as LU factorization. There are infinitely many LU factorizations of an invertible matrix A because if A equals LU, and D is any invertible diagonal matrix, then A equals L times D inverse times D times U, giving a new LU factorization by the matrices L D inverse and DU. This fact means that we can decompose an invertible matrix A into the product of a lower triangular matrix L and an upper triangular matrix U, whose diagonal entries are all ones. This is known as a Crout decomposition. Before we look at the specifics for the algorithm for Crout decomposition, let's do a high-level overview of how this algorithm works. If our matrix is n by n, our algorithm will require n passes, where each pass is made up of two parts. The first part of the kth pass will give the kth column of L, and the second part of the kth pass will give the kth row of U. On the last pass, we only have to do the first part to determine the nth column of L, because the nth row of U is already known from the start. Now suppose that we've solved for the L and U matrices. Then the entry in row I and column K of matrix A equals the dot product of the ith row of L with the kth column of U. Note that because of the structure of L and U, this dot product, when written as a sum, will have many zero terms. The number of non-zero terms will be the minimum of I and K. Now this expression holds for any I and K, but since the two cases I less than K and I greater than or equal to K correspond separately to the entries of U and L respectively, it helps to separate this sum into two cases, one where I is less than K and one where I is greater than or equal to K. The next observation we're going to make is basically the foundation of the Crout decomposition algorithm. Suppose I is less than K, and we've already determined all rows of U up to but not including row I, and also suppose that we've determined row I of L. Then we can take the ith term out of this sum and solve for the unknown entry U sub I k, which is the entry in row I and column K of U, in terms of the known entry in row I and column K of A, and the other entries of L and U that we just assumed to already be known. Similarly, if I is greater than or equal to K, meaning we're in the lower triangular half of our matrix, and if we assume that we have determined all columns up to but not including column K of L, and that we have already determined column K of U, then we can take the kth term out of this sum and solve for the unknown entry in row I and column K of L in terms of the known entry in row I and column K of A, and the other entries of L and U that we assume to already be known. The formula in blue and the formula in red are exactly the formulas used in Crout's method for finding an LU factorization. One last observation is needed to give us the Crout decomposition algorithm. These formulas only allow us to solve for a given entry of L or U if we've already solved for all entries of L and U that are required so that the only unknown in the formula is the entry of L and U that we're trying to find, the one on the left-hand side. Now, if we set K equal to 1 and I is greater than or equal to K, we do satisfy the assumptions that let us say L sub ik is the only unknown in the red formula. This is because there's no column 0 of L, and column 1 of U is determined from the start, from how we constructed U. Using the formula, we can now solve for the first column of L, that is the entries L sub I1. it ends up being the case that the first column of L will always be the first column of A. Next, building off what we have so far, which is part 1 of pass 1, if we set I equal to 1 and k is greater than I, then we satisfy the assumptions in the blue formula. There is no 0th row of U, and row 1 of L has now been determined. We can now get the following formula for U sub 1k, which is the first row of U. This completes our first pass. Note how the result of the first part of the pass, that is, the next column of L, was needed to solve for the result of the second part of the pass, which is the next row of U. If we continue in this way, we will eventually find L and U. This is Crout's method for finding a LU factorization. Let's do an example now. On the screen, you can see our matrix A, along with the formulas that we should use for each pass, with the red formula used to find the next column of L, and the blue formula used to find the next row of matrix U. Once again, applying the first formula for the first pass is easy. We get that the first column of L equals the first column of A. We can also apply the second formula to determine the first row of U as before. Now let's begin our second pass. In the first formula, we fix k equal to 2, and to find L sub ik, where I is anywhere between k and n because otherwise we already know L sub ik equals 0, we will subtract from A sub ik the sum from m equals 1 to m equals 1 of L sub im times U sub mk. Another way to think about this is that we know A sub ik is the dot product of a row vector from L with a column vector from U. So with that, we just rearrange terms to solve for the only variable appearing in this dot product that is not already known, where the row vector from L is the ith row of L, and the column vector from U is the kth, or equivalently the rth column of U, where r equals the current pass number. The dot products of rows of L and columns of U that underlie the formula we're using at any given time are going to be highlighted in yellow from this point onwards. Applying our formula, we find that L sub 2 equals negative 3, L sub 3 equals negative 1, and L sub 4 equals negative 1. We have now determined the second column of L and completed the first part of our second pass. To complete the second part of our second pass, after using the formula, we get the following result for U sub 3. Applying the formula to the other entry of the second row of U, we end up getting the same result. We've now completed the second pass. For the first part of our third pass, we fix k equal to r, which is 3. Using the red formula to find L sub 3, we get 13/9. Using the red formula to find L sub 4, we get negative 17/9. For the second part of our third pass, we fix I equal to r plus 1, which in this case is 4, to find U sub I4, where I goes from 3 to 3. In other words, we only need to find U sub 4. Using the blue formula, we get a result of 1. For the first part of our fourth pass, we fix k equal to r, which is 4. Using the red formula to find L sub 4, we get 2. We're now finished. The Crout decomposition is as shown on the screen. You can check this by multiplying L and U and making sure they equal A. In summary, Crout decomposition is a special case of LU factorization where the upper triangular matrix has all 1s on the diagonal. The algorithm for Crout decomposition uses the formulas shown here. It requires n passes for an n by n invertible matrix. And in each pass, we first find the next column of L, and secondly, the next row of U. Note that to save space, you can overwrite the entries of A with your results for L sub ik and U sub ik, because the entries of A that are involved in the calculation of U sub ik are not involved in the calculation of L sub ik, and vice versa, and each entry in A is used to compute a single element of U or L. To see what this looks like, here's a diagram illustrating the Crout decomposition with rewriting of the matrix of A at some intermediate pass of the algorithm, where the colors represent different kinds of entries for the purpose of our algorithm. The arrows represent dot products being taken of row or column vectors. That's all for this video. Thanks for watching.